Let's take a look at section 4.3, properties of logarithms. We're going to use these three properties where m is bigger than 0, n is bigger than 0, b is bigger than 0, different from 1, and p is any real number. The product rule says the base b log of m times n is the base b log of m plus the base b log of n. That comes from the fact that b to the little m times b to the n is b to the m plus n. So when you multiply exponentials, you add exponents. Remember, logarithms are exponents. So when I multiply the input, I'm adding the exponents. The quotient rule comes from the fact that b to the m divided by b to the n is b to the m minus n. So the base b log of m over n is the base b log of m minus the base b log of n. The power rule comes from the fact that b to the m to the p is b to the m times p. So the base b log of m to the p is p times the base b log of m. So these are the rules we're going to use to expand logarithms. And notice that b to the m is capital M, b to the little n is capital N. And that's the connection between the lowercase m and the capital M, the lowercase n and the capital N. Let's look at our first problem. We want to use the properties of logarithms to expand the logarithmic expression. Wherever possible, evaluate logarithmic expressions. So the first thing we're going to do is rewrite this fifth root as a power of 1/5, because the nth root of b is b to the 1 over n. So that's a fact from intermediate algebra, and that's what we're using here. So first, we're going to use the power rule. And that basically tells me that 1/5 is going to get multiplied by the base 4 log of x to the squared y to the 5th over 16. I could use the product rule next, but I'm going to choose to use the quotient rule next. So 1/5 is multiplied by, and notice how I need to group this, the base 4 log of x squared y to the 5th minus the base 4 log of 16. So notice that that's the quotient rule, and that 1/5 has to be multiplied by this difference. So I have to group the difference with the brackets. So 1/5 is multiplied times the base 4 log of x squared y to the 5th minus 2, since the base 4 log of 16 is 2. The exponent I apply to 4 to get 16. So the product rule will now be used. So I use the product rule to write the base 4 log of x squared y to the 5th as the base 4 log of x squared plus the base 4 log of y to the 5th. And I'm going to now use the power rule again. So base 4 log of x squared is 2 times the base 4 log of x. Base 4 log of y to the 5th is 5 times the base 4 log of y. Now I'm going to use the distributive property. And 2/5, 2 times 1/5 is 2/5. 5 times 1/5 is 1. 2 times 1/5 is 2/5. So this gives me my final simplified answer. The log is completely expanded. All right, let's use the properties of logs to expand the logarithmic expression. Wherever possible, we want to evaluate logarithmic expressions. All right, now remember, this log doesn't have a written base, and the abbreviation for log is log. So this base is 10. This is called a common logarithm. So I'm going to use the quotient rule first. So the common log of 10x to the fourth, and I'm going to write the square root of x plus 7 as x plus 7 to the 1/2, minus the common log of x squared minus 25 to the third. So that was just the quotient rule. Now I'm going to use the product rule for the first part of this expression. So the common log of 10x to the fourth plus the common log of x plus 7 to the 1/2 minus the common log of x squared minus 25 cubed. So notice, since the first two input, the log expression had a product, I could write that as a sum of logs. So now I'm using the power rule. 4 times the common log of 10x plus 1/2 times the common log of x plus 7 minus 3 times the common log of x squared minus 25. I'm going to use the product rule again. 4, notice how I need to group this, sum, times the common log of 10 plus common log of x plus 1/2 common log of x plus 7 minus 3 times the common log, and I'm going to factor this, x squared minus 25 into x minus 5 times x plus 5. So let's use the product rule again for the 3 times common log of x minus 5 times x plus 5. And let's evaluate the common log of 10, which is 1. The base is an unwritten 10, so 1 is the power I apply to 10 to get 10. And I'm going to put a grouping here around this product in the previous step. And notice how I now have to group this sum, common log of x plus 5, added to the common log of x minus 5. And now let's use the distributive property. And we get our final completely expanded version of the logarithmic expression that we started with. All right, another thing that we'll need to do sometime is condense logs. So we'll start with an expanded form, and we'll want to write that as a condensed form. And again, m and n and b are positive, b can't be 1, and p is any real number. P can be any real number. All right, so we're going to really just be using the power, quotient, and product rules again. But now we want to use them to condense a logarithm rather than expand it. Okay, so here we're going to use both the product and the quotient rule. The logs that have a positive coefficient are going to go in, the input to that log is going to go in the numerator. The input to the log with a negative coefficient is going to go in our denominator. So x squared minus 5x plus 6 and x plus 2 are in the numerator of this base 9 log. And then the x squared minus 4 is in the denominator. So I've used both the product and the quotient rule here to condense. And now I'm going to factor x squared minus 5x plus 6 into x minus 2 times x minus 3. Recopy the x plus 2, And I'm going to factor x squared minus 4 into x minus 2 times x plus 2. And I'm going to divide out the common factors. So I'm left with the base 9 log of x minus 3. That's my final answer. It turns out this next problem is actually the exact same problem. We won't work that twice. So we'll go on to the change of base property, which basically says for any logarithmic basis a and b and any positive number m, the base b log of m is the base a log of m divided by the base a log of b. So in other words, this allows me to eliminate using a base of b if that's not convenient for me. And typically this is the issue. Your calculator that will be allowed on exams will only have base e or base 10 natural or common logarithms. So let's look at, where does this come from, you may wonder. Let's look at a proof of this property. Well, we're going to start by calling the base b log of m y. That allows us to write the equivalent exponential equation b to the y equals m. So let's apply the base a log to b to the y and also to m. Now let's apply the power rule to the base a log of b to the y, which gives us y times the base a log of b. Let's solve this for y. So we're going to divide both sides of the equation by the base a log of b. And we find that y, which we said was the base b log of m, is the base a log of m divided by the base a log of b. So that is where the change of base property comes from. So on your scientific calculator that you'll be able to use on exams, you're going to have an log or common log key and a natural log key. And if you're given an expression such as common log of 50, you can calculate that. Or natural log of 319. You can calculate that with the calculator and you get these approximate values. So common log of 50 is about 1.69897. Natural log of 319 is about 5.76519. But you do run into a problem if you try to calculate the base 3 log of 10. So remember the change of base formula, the base b log of m is the base a log of m divided by the base a log of b. Well, that, if I'm using common logs, that would be the common log of m divided by the common log of b. If I'm using natural logs, that's the natural log of m divided by the natural log of b. And those are typically what we're going to be using. Those are the logs on your calculator. So let's use the common log to calculate the base 3 log of 10. So that's the common log of 10 divided by the common log of 3. Well, the common log of 10 is 1. That's the exponent I apply to the unwritten base of 10 to get 10. So I really just need to divide 1 by the common log of 3. So I use my calculator to do this. And you want to make sure you know how to use your calculator to do this type of calculation. Please let me know if you're having trouble with your calculator. So we can actually check to see, is 2.0959, I rounded this to the nearest to 4 decimal places. So let's check and see if this is correct by simply, the base 3 log of 10 is the exponent I applied to 3 to get 10. Since I rounded that off, I get something close to 10, 9.99996408, and that is about 10. Okay, so the change of base formula allows me to use the bases available for calculation on my calculator. So if I want to find the base 9 log of 200 using base E logs, I calculate the natural log of 200 and divide it by the natural log of 9. And I'm going to round it to 4 decimals, 2.4114. So I'm going to check this by raising 9 to the 2.4114 power. Remember, the log is an exponent. So in this case, I want the exponent I apply to 9 to get 200. Now notice I'm going to get something a little bigger than 200 because I rounded up. But 200.0139963 is very close to 200. So let's use base 10 to find the base 16 log of 57.2. So we're going to divide common log of 57.2 by common log of 16 and round our answer to the 4 decimal places. So we get 1.4595. So we rounded that up. So we can check by applying that log value, remember the log is an exponent, to the base of 16. See if I get approximately 57.2. Since I round it up, I'm going to get something a little bigger than 57.2. But notice how close this result is to 57.2.